Good morning, everyone. Welcome to the Ninth Electron Devices and Solid-State Circuits online seminar. So today, we are very honored to have Professor Bing Gao here. So he's now associate professor with the Institute of Microelectronics at Tsinghua University. He received his bachelor degree in physics from Peking University in 2008 and a PhD degree in microelectronics from Peking University in 2013. In 2015, he joined Tsinghua University as an assistant professor. His current research interests include modeling, design, and fabrication of emerging semiconductor devices, especially RRAM. So he has published more than 100 technical papers, including 38 papers on IDM, RSSCC, and VLSI, as well as several journal papers on Nature Electronics, Nature Communications, Proceedings of IEEE, etc. His total citation is over 6,000. He was a recipient of the IEEE EDS Master Student Fellowship in 2009 and a recipient of IEEE EDS PhD Student Fellowship in 2012. He received the China Industry University Cooperation Innovation Award with Gig Device in 2017. He serves as Modeling and Simulation Subcommittee Chair of EDTM 2021 and the Technical Program Committee members of IDM, DSE, IRPS, etc. So without further ado, let's welcome him to give this seminar. Professor Gao, you can start now. Professor Gao, you can start now.
Our recent work on computation in memory. So just now, Qiming introduced me. My name is Bing Gao from Tsinghua University. I'm now the associate professor in the Institute of Microelectronics. Today, my talk title is Design and Optimization of RRAM-based Computation in Memory. Okay. Okay, this is the outline of my talk. The presentation includes 5 parts. First is the introduction. In the recent years, the data are generated very fast, brings great challenge for the computing system. In this figure, the black dot shows the increasing trend of computing power of CPU and GPU chips. We can see the computing power of CPU increased exponentially before 2010, but went to saturation recently, while the GPU provided another solution for the computing power development, but also shows saturation now. On the other hand, the computing power requirement for the AI training grows very fast. After 2010, this requirement doubled almost every 3 to 4 months. It is clear that the saturated computing power cannot meet the requirement of AI application. So why increasing the computing power is difficult? One reason is the MOSFET scaling issue. As the IC fabrication process goes to sub 5 nanometer size, the Neumann architecture. In this architecture, the computing unit and the memory unit are physically separated, and the data need to transfer frequently between the computing unit and the memory unit through buses. So in this case, the data transfer and the memory access consume a lot of useless energy and time. This is the so-called memory wall issue. This figure shows that such data transfer may consume more than 60% of the energy during a general purpose computing task. Well, for the data-intensive task, such as AI computing, the cost on data transfer may be higher than 99%. neural network is a typical data-intensive task. Even a typical light network may contain hundreds of megabit weights and need giga-level MAC operations for GPU, and then the processing near memory technique were used on the TPU. However, to further increase the computing power and reduce the area and the energy consumption, the emerging technology such as computing in memory should be introduced. Here we call it CIM for short. We first show an example on how to realize CIM with RRAM array. The computing task is a vector matrix multiplication, which is a basic operation in a neural network algorithm. With a RRAM array, it is very easy to finish this computing. We just map the input vector as the applied voltage on the array, and the weight matrix is mapped to the conductance of RRAM array. Then the output current is the result of the matrix. And either and 6 memory cell, so it is very efficient. With CIM architecture, we can combine the computing unit and the memory unit into one SIM unit. The key research task for CIM are how to develop analog RRAM device with good analog switching performance, and how to find new computing paradigm for the CIM. Here, I need to emphasize that the analog switching behavior is important for CIM application. So different from the traditional binary RRAM device, the analog RRAM has multiple stable states. We can tune the device conductance by applying different numbers of pulses. In the second part, I will talk about the recent research progress and the challenge of this area. The CIM research experienced 3 stages. During the first stage, people mainly focus on the device optimization. For example, the HP from UMich developed electric synapse with analog switching behavior. And Professor Philip Wang from Stanford University demonstrate analog RRAM with good performance. After 2013, people began to focus on array demonstration. Several AI tasks were proposed on kilobit level arrays. For example, the UCSB demonstrate a 12 by 12 array for the cartoon letter recognition. And our group demonstrate a 128 by 8 array for the human face recognition. And also UMass, IBM also do some similar demonstration. So these achievements were from different units and published on some microchips, microcircuits have been designed and fabricated. The integration level increased to megabit, and more functions were realized on hardware. So these chips were reported on VLSI and ISACC. In summary, in the past 10 years, we have seen significant achievement on device development, CIM function demo, and circuit design. However, a complete CIM system is still challenging. Here we summarize some key challenges. On the device level, the challenge mainly focuses on the reliability issue, including the yield, uniformity, retention, and endurance. And on the system level, one challenge is how to fight against the accuracy loss. Another challenge is how to patient. All these challenges are originated from one reason. This is the lack of design methodology for analog RRAM device and the CIM system. So here we develop some EDA tools to solve the above issues. These slides show the overall framework of our EDA toolchain. We have developed a KMC simulation method and a multi-scale simulation framework for the device level optimization. And we also propose some system level simulator, emulator, and compiler for the CIM circuit and the system design. Now I will first introduce our work on device level simulation. The analog RRAM for CIM application is much more complex than binary RRAM for the data storage application. And for learning the learning case, the device requirements are also quite different from inference only case. So here we show our we show their performance requirement. We can see the data storage application only focuses on reliability issue like yield, retention, and endurance. But CIM applications need to realize multiple states and a large of ratio. And for the learning case, the linearity and symmetry of the conductance tuning are also important. So our work, our first task is to achieve stable analog switching behavior. And after that, we change to study how to improve the reliability of analog RRAM. Although some types of analog RRAM device have been developed in the previous work, realizing stable analog switching is still a difficult task. Many previous devices were based on interfacial switching mechanism. These non-fragmentary type RRAM devices are easy to get analog switching behavior, but the retention is poor. Sometimes we can even see the resistance drift in the time scale of seconds to minutes. Meanwhile, the switching speed of interfacial RRAM is not good. We can see the speed usually is very slow. If we increase the speed, the retention will degrade significantly. So there's a difficult trade-off. On the other hand, the fragmentary RRAM can achieve very fast speed and long retention time at the same time. But the fragmentary conduction and rupture mechanism limits its analog switching ability. So typically, the fragment RRAM can only show analog switching during reset process, but set process is very abrupt. So we need to find new ways to get stable bidirectional analog switching. So here we develop a kinetic Monte Carlo simulation method. So here we first construct a device structure. The switching layer is hafnium oxide. There is a capping layer on top of the hafnium oxide layer. Besides, we also consider the top and the bottom electrodes, as well as the silicon oxide surrounded by the switching layer. So this is a typical RRAM device structure. And the simulation flow is shown here. We first calculate the electric potential and the current density distribution via finite element method. We also calculate the thermal and temperature distribution inside the filament region. After that, we can get the matrix of several probabilities, including the generation, recombination, and migration of oxygen vacancies and the oxygen interstitials. Then we can get the vacancy distribution with Monte Carlo method. And we can repeat this calculation process to get the evolution of oxygen vacancy distribution. We start from the physics-based model. The set process is attributed to the generation of oxygen vacancy under electric field and thermal activation, forming conductive filament. The filament can be either metallic or tunneling, depending on the density or average distance of oxygen vacancies. The reset process is caused by the oxygen ion releasing from the active electrode or the capping layer, and then recombined with oxygen vacancies, resulting in the rupture of the filament. These are some related equations for this physics-based model. Here we can see the KMC simulation results on a RRAM device with traditional structure. The yellow dots are the oxygen vacancies. During set process, a filament is formed and gradually becomes strong. With this simulation tool, we find the internal temperature is a key factor for the switching process. On the traditional device structure with a metal capping layer, the internal temperature during switching process is not so high. You can see it's about 500 K. While if a capping layer is changed to a low thermal conductivity material, the temperature can be enhanced. We call this material as the thermal enhanced layer, or TL. It is a submetal oxide with low thermal conductivity and high electrical conductivity. We can see with this TL, the internal temperature increased significantly from 500 K to nearly 800 K. So in this case, the oxygen vacancy do not gather together. The KMC simulation results show that after introducing this TL, vacancies are more likely to be scattered. No strong filament is observed. As the set process goes on, the oxygen vacancy density increases. This figure shows the oxygen vacancy generation probability distribution during set process. So it can clearly illustrate the mechanism of multi-weak filament formation. So without TL, only several key points have the highest vacancy generation probability. Around these points, the local electric field is very high. So the oxygen vacancy generation is electric field control. While for the with TL, the vacancy generation changed to temperature control. So the distribution is more uniform. So in this case, the vacancy can be formed at any place with similar probability. So in this case, we can see the scattered vacancy distribution. These slides show the current path distribution of the two devices. Without TL, it is obvious that only a strong current path is formed. But with TL, there are many weak current paths formed by percolation effect. Each weak filament can contribute a little to the device conductance, and therefore resulting in controllable analog switching behavior during both set and reset process. With this design guideline, we fabricate analog RRAM device and integrate into kilobit level 1T1R array. We get very good performance on this array. This figure shows the conductance tuning characteristic with identical pulses. Both set and reset process showed excellent analog behavior. Each level is very stable under even under very high baking temperature. Here I only show 4 levels, but in fact we have measured many levels throughout the array. After developing this analog RRAM device, we changed to study its reliability. It should be noticed the reliability characterization method of analog RRAM is also quite different from the binary RRAM. For binary RRAM, we only focus on the whether the resistance window is existing or not. However, for analog RRAM, we have to monitor the conductance change at any time point. So for retention, disturbance, and noise test, it's much stricter. On the other hand, from the modeling view, the reliability study is also more difficult because we need to find a way to cover the broad spatial temporal scale. In another word, we need to link the atomic event on the picosecond and the Armstrong scale to the device behavior on the seconds and the micrometer scale, and to the array reliability on the years scale. Another challenge is that many reliability issues are correlated with amorphous effect, but many modeling work only treated the switching layer as a crystalline material. So to solve all these issues, we develop a multi-scale framework. The simulation starts from the molecular dynamics. We first use MD method to generate the amorphous hafnium oxide structure, and then use the DFT to do the structure optimization. We also use DFT to calculate the distribution of activation energy on the different lattice point and getting the distribution matrix. And then we input these calculated parameters to the KMC simulator and finally calculate the device electrical behavior and reliability characteristics. With this method, we identified some key migration paths related to the amorphous material, which contribute to some reliability degradation behaviors. We also show that the oxygen vacancy distribution is quite different in the crystalline case and the amorphous case. More detail can be found in this year's IEDM. Okay, let's go to the next part, device system co-design. The design of CIM system also faces many challenges, especially the accuracy loss caused by non-ideal effects of device and circuits. On the device level, the parameter variations, conductance fluctuations, nonlinearity, symmetry, and other non-ideal effects will influence the computing accuracy. And on the array level, the fluctuations accumulate, forming larger error. Each array error can further accumulate layer by layer, forming significant system-like error. For example, if we only introduce 1% error on each layer of a ResNet, the error of the whole network can still increase to almost 100%. So this error accumulation only occurs in the analog computing, but it's the key challenge for the CIM. Another challenge is the array-to-array communication issue. If we use a lot of data converter and cache, the energy consumption and the chip area cannot be accepted. But without data converter and cache, we cannot ensure the computing accuracy and the reconfigurability. It is clear we cannot eliminate all these effects from a specific level design. So the co-design from device level to system level is highly required. We first develop an end-to-end simulator from device level to circuit architecture and algorithm levels. The device level consider the physics-based compact model, including many non-ideal effects. So we can perform high-level design with considering all the bottom-level constraints. This is our compact model. It starts from our KMC simulation results. We make some necessary simplification and thus get the analytical equations. The physics picture is still from a multiple weak filament view. Each filament can be either metallic or metallic dominated or tunneling dominated. The evolution of multiple filament is caused by oxygen vacancy migration. In this case, we can capture the dynamic analog switching process and its non-ideal effects like variability, nonlinearity, voltage sensitivity, and so on. We also extract a transistor model because our array is a 1-to-1R array. Then we develop a micro circuit compiler for the CIM system. This compiler includes the above compact model of RRAM device. And at the array level, we have considered the error drop caused by the interconnect resistance and the snake path issue and other array effects. We also designed the periphery circuits such as ADC, DAC, MUX, SFU, shift adder, and so on. And include this circuit model in the compiler. The ADC and DAC precision and other circuit constraints are all included. So with this compiler, we can get performance of the CIM circuit. This is for the micro circuit with different parameters and find the best design space. And then we further develop a cross-layer simulation tool. This is an end-to-end simulator from algorithm level to the basic device and micro circuit level. The network compiling, matrix split, the weight placement, weight mapping, and weight programming, and the matrix multiplication process are all included. So this is the first fully silicon verified simulator for the CIM. We also use it to, we can use it to benchmark chip area, energy efficiency, and accuracy and latency of the CIM system. We can also use it to do some algorithm benchmark and architecture design. We also developed the complete software stack for CIM system. The software and hardware have good compatibility. Besides, the training and compiling can be done in our simulator. Besides the software-based simulator, we also develop a hardware-based emulator. This emulator contains multiple CIM micro board. Each board contains an analog RRAM array and some periphery circuit. on the PCB board. And other peripheral circuits are on the main board. The FPGA is used to control the whole system. With this hardware emulator, the benchmark for the CMOS system can be more accurate. We can also use this emulator to verify our simulator. So just now, I mean, our simulator is fully silicon verified because we have this hardware emulator. And besides, this emulator is still very flexible. It's flexible enough because we can change the peripheral circuit very easy, and we can also change different RRAM array design. We just need to change some PCB board here. So it is very flexible. We can change the architecture and some circuit to do various benchmarks. With these design tools, we propose many novel methods to achieve the high computing accuracy. And we also design and fabricate a full system integrated CMOS chip. This is the first full CMOS chip based on analog RRAM array and CMOS transistor mix integration. It is fabricated with 130 nanometer process and contains 160 kilobit RRAM cells. It can perform MLP for pattern recognition task. The energy efficiency is as high as 68.4 TOPS per watt. We should notice that it is the full system energy efficiency, not the array macro efficiency, energy efficiency, as reported in many previous papers. So it is the full system. So we have demonstrated a very high energy efficiency. Now I show the functional demo on this CMOS chip. We developed this demonstration system with an FPGA board and an interface. It can show the computing power consumption and the results in the real time. We can handwrite some digital patterns on the table lid, and then the patterns are sent to the chip. The chip is here, and the chip sends back the computing results as shown here. In this demonstration, we use MNIST dataset for training, and we can write any digital numbers by our hand for the testing. So it is very easy. Finally, we design a full CMOS system with multiple analog RRAM array. So this is one RRAM array, and here you can see on this PCB we have multiple RRAM array. The system includes 8 array macros and all the other peripheral circuit. The energy efficiency is more than 10 TOPS per watt, about 2 orders larger than a GPU. Here we also show the whole architecture design for this CMOS system. We use this CMOS system to process a CNN task. And we develop a new hybrid training method to fight against the error accumulation issue, because we meet the key challenge is how to recover the computing accuracy. So here, first we do a pressure training executely on an execute computer. This pressure training use our end-to-end simulator as the training tool. So during the training process, all the non-ideal effects from the device level and the micro circuit level are all already considered. So the trained weight, the weight after training, are more robust. It can immunity to many variations. And after execute training, we transfer the weight to the RRAM array with a closed loop programming scheme. Of course, the writing process is not so accurate due to the device variation and some reliability degradation. So we then perform in situ training on the hardware. During in situ training, only the last fully connected layer is tuned, while the other layers are maintained unchanged. Only a small portion of the training set is needed for this in situ training, because all the weights have been already well in situ trained. So this in situ training only need very small cost, which means we only need a small data set and only need to tune one layer. So this training is very fast and do not need to cost much energy. With this hybrid training method, the computing accuracy of the CIM system can be recovered to the near software level. Finally, I'd like to discuss the future outlook. We hope to develop a new CIM computing system. In this system, we introduce revolutionary change from device level to compiler level. The semiconductor device change from transistor to the analog RRAM combined with the transistor. And the computing paradigm change from digital Boolean logic to the analog computing based on physics law. Here I mean physics law because our computing is based on the Kirchhoff's law for the addition operation and with the Ohm's law for the multiplication operation. So it's all based on the physics law computing. The architecture combines the memory unit and the computing unit together. So it is a non-von Neumann architecture. However, we do not hope the users of the computer do not feel this significant change on the hardware. So the software and the programming language should be maintained the same as the classic computer. So we also need to do more on the compiler and the instruction sets. We need to do to research some new compiler and the instruction sets for the CIM computer. The cross-layer design for the network mapping and the analog computation algorithm technology are needed. This new computing system is able to enhance the energy efficiency for 2 to 3 orders, reaching 100 TOPS per watt to 1 POPS per watt. That is our hope. To achieve this goal, the EDA toolchains are very critical and highly required. In our recent review article on Nature Electronics, we propose a framework for the complete EDA toolchains from the user level to algorithm level, architecture level, macro level, and the device level. We also need to clarify the interface between each EDA tools. For example, the interface between device and array, between array and architecture, between the hardware and the software, so on. In the last slides, I share our views on the future roadmap. In the past years, we saw significant achievement on the analog RRAM devices and microchips. But in the long future period, we still need to let me see, the pointer is go so slow. So in a long future period, we still need to improve the device performance continuously. This is a long time work, maybe takes more than 10 years, I think. And especially we need to focus more on the reliability issues. And we also need to do more explorations on the neuromorphic device, such as the artificial soma and artificial dendrite. We need to find the new theoretical integration method to integrate these different neuromorphic devices on one chip. After developing the useful EDA tools, we can design full functional SoC chip for more general purpose AI processing. Because currently our chip can only process some MLP or CNN, but the neural network or some AI algorithm almost change every year, change year by year. So we hope to do some general purpose AI chips which can process different algorithms. So I think this relies on the EDA tools and also relies on the device optimization. And in the far future, we can expect all brain inspired chip and 3D integration technology. I think in this way, our chip can be more powerful. These are our recent research paper on RRAM modeling and the CIM system design. These are our recent review articles from different perspective view for CIM technology, including the CIM chips in memory learning, CIM reliability, neuromorphic device, RRAM model, and mechanism. That's all. Thank you very much for your attention.
So thank you, Professor Gao, for giving such a wonderful talk. It almost covers every perspectives of computing in memory systems. It's very inspiring. So now it's Q&A time. So you can raise your hand, and I will ask you to speak up in sequence, or you can just type your questions in the chat box, and I can ask on behalf of you. Okay. Okay, maybe I can start by asking one question. So you mentioned that we needed to have a very linearly programmable RRAM device. Can you briefly explain why we needed this kind of device for learning?
Okay. So you mean this linearity? We need this optimize this linearity.
Yes.
So for this, this is a typical weight update curve for measure the analog RRAM device. To measure this curve, we just apply the identical pulse, and the conductance will change pulse by pulse. So if we apply the side pulse, the conductance will change. And if we apply negative pulse, the conductance will decrease. We hope this change, I mean the conductance on pulse number, this change should be linear, because the linear means with each pulse, the delta T, I mean the conductance change is constant. So in this case, to do the training, we can expect for each weight update process, we can expect the change of weight. So in this case, the network is more easy to converge. But if the change is very nonlinear, that means at first the conductance change very fast. So with one pulse, maybe the change can be found more than 50% throughout the whole window. So in this case, it is difficult to make the network converge. So I think this linearity is very important. And in fact, there's a lot of work on this type of simulation. We just use this weight update behavior model to do some network simulation. All the work found this linearity is have significant impact on the network training.
So okay, so can I understand that it's already a kind of software hardware co-design? So this linearity requirement is really from in the convergence, like a software requirement.
Yes,
okay.
Yes,
see.
yes, you are right. This is a software hardware co-design. And in fact, maybe if you design some network more robust, maybe it can afford some type of some kind of nonlinearity.
Thank you. So let's see. Please ask questions. Oh yeah, we have one.
Hi, Professor. I have a question.
Yeah, go ahead. Yeah.
Okay. So you've mentioned that one of your major. So I'm just curious because you've mentioned that one of your major outlooks is to be able to achieve a CIM computer, right? I'm just wondering because one of the emerging neural networks these days is the spiking neural network. But based on this presentation, most of the computational solutions that I've seen focuses more on non-spiking based neural networks such as CNN. So how do you think will your framework will change, or how will the spiking neural network based computation will influence this entire computing system? Because I think that the analog computing part is going to be is different compared with the non-spiking based neural network. So how do you think SNN will influence this entire framework? Thank you.
Oh yes, it's a good question. In fact, I think the analog computing and the spiking network, there's two different technology ways, and I think these two ways are all important. For example, in our brain, the vision system is based on the analog computing, but the decision system is based on spiking. So I think this both the analog computing and spiking, we need to do some research. So for here, we only mentioned in my talk, I only mentioned the analog computing because the SNN algorithm is not so mature as the CNN. The computing accuracy is not as good as CNN. So our research now only focus on the CNN, but for spiking, I think there's also some algorithm work. They can transfer some CNN to the SNN. So in this case, we can also use our CIM chips for this kind of computing. We just design some chip which can the input only the input is changed. So for this spiking chips, we do not need DAC for the input. We just need to design I don't know how to say that word in English. I mean the 异步电路异步电路. I don't know how to say that. We just need to design some different input circuit. But the RRAM array and the output are all similar. So in this case, we can make our chip, not computer, we can just make our chip to support both the non-spiking and the spiking computing. And so our computer can also support that. But this is based on the network transfer. If you think the more brain-spared SNN, I mean, if you hope to support some STDP or some short-term memory, I think we still need to develop some novel device, some neuromorphic device to support that. I think it's a much long way. We need a much long way to go because currently this kind of work are still only stay on the device level. We do not see much work on the circuit level.
Yeah. Okay. Thank you so much.
Great. So we have a few questions in the chat box. I think this first question is actually what I also want to ask. Okay. So can I ask how to access your model, simulator, and the compiler. So, or if it's even possible, I know that you have a very large group at Tsinghua University. Your group has encapsulated very good, like software simulator, hardware simulator, and some models, right? So which cannot be done by any other single group. So I'm wondering if your system is open to others, like if yes, how could others prepare their models and devices to be tested on your simulator, something like that, right? So can you try to address this question?
Okay, that's a good question. In fact, we have already uploaded some of our simulator online. We hope to share our work to the public. So currently, we already upload this end-to-end simulator to the GitHub, and I think in the maybe in the next few months we will construct our own website for our group. So currently, our website does not work well. So someone also sent email to me or to the Professor Huaqiang Wu to ask for our code for some simulation, for some simulator. So in this case, we typically we all send the code to them. But I think after several months, we can upload to our website and you can download. So here, I think we will share our the device compact model. So use this model, you can do some device level simulation, and we will also share our micro compiler and the end-to-end simulator. And we also have a plan to share our hardware emulator. So this thing we have already considered for 2 years because we hope to spread this area. So we hope more groups can do some hardware demonstration. We have this plan, but due to the time limit, we found to fabricate one this simulator. This is the emulator. It is very time consuming, almost costs us 2 months. So if we open this to public, maybe all our group need to do this every day. So just now, if someone want to use, you can come to our institute. We can let you try it in our lab.
Great. Okay, so you can raise your hand and speak up. So there are some questions in the chat box. I will continue to read it. Okay. So the second, another question is about modeling. Okay. How do you actually make your model more accurate? Right. So this is how to improve your model accuracy. I think another question is about binary RRAM as a storage like memory. So for a large capacity memory, like if you want to achieve 10-year lifetime, for single cell, you need to have 4.8 times 10 to 17 cycle in duration, which is impossible for RRAM. What do you think if we can do to solve this problem? I think in general, these two questions about the accuracy of the modeling and the reliability of a single RRAM device. Yeah, can you address this too?
So the second question, to my understanding, you want to ask how to improve the reliability of analog RRAM. So here, I think we can first talk about the endurance. For the endurance, we mainly focus on the training because training we need to change the conductance time by time. But this change is not the same as the binary RRAM. For binary RRAM, all the programming is the full window programming. That means we need to change the device from the lowest state to the highest state. But for the training application, we just tune the conductance little by little, only a slight change. So in this case, the electric field is not so high as the full window programming. So its damage is small. We already do some this type of test. We find if we only do this small conductance tuning, the endurance can be improved for several orders. So we already measure all the measure from the array. We found the endurance can be improved to more than 10 to the power 11 cycle. So I think do not need to care about the endurance for the training application because it's only tuned a little. And for retention, it's a problem because binary RRAM, we do not care about the conductance change. We only care about the window. So only if, although the conductance change by time, but the window still exists, that is no problem. But for analog, for the analog RRAM, only slight change of the conductance may cause the computing error. So in this case, we hope the state very stable. That is very difficult. We still find ways to make it stable. But another thing, I think, that is the bad thing. And for the good thing, we do not need to get a 10 years retention. I think no need. For storage application, of course, 10 years is required. But for this neural network application, maybe I think maybe 1 day is okay, or maybe 1 month is okay. No one knows, depending on different application. For example, if our network can support some training, if some cell the conductance change a little, I mean some retention degradation, you can find the network, the accuracy of network decrease. But now we can do some training. This training is not from the beginning, just a hybrid training, just tune a little. So in this case, we can recover the network. So I think the training is a good way to solve the retention issue. So this is also a software hardware co-design. I think this is your second question. The first question, you mean how to keep the accuracy of our model? I don't know how to answer this question. For our model, we all start from the physics, from the microscopic picture, and after construct model, we do a lot of data fitting from the experiment results. So for our model work, in fact, we most of the time host on the array measurement and data fitting. I think this is very important.
Great. So we have another question. So are analog RRAM devices fabricated on the same wafer with the peripheral circuit? So because CMOS circuits can also achieve such a synapse function, what is the advantage of your RRAM compared with to CMOS synapse at present? CMOS synapse can have a longer lifetime and much better compatibility with CMOS devices.
CMOS synapse, if you use a CMOS circuit to realize the synaptic function, I think this circuit is maybe very complex, not as compact as a RRAM device. For the neural network application, we hope the synaptic density very high. So in this case, I think single device is much better than a complex circuit. But if you mean some transistor-based synapse, I also see many work on this. They propose use one transistor to emulate the synaptic behavior. So this type of work, I think, also very interesting. Maybe in the future, we still do not know whether the synapse we use RRAM or PCIM or FEFET or some transistor for the synaptic application. So I think we can also do a lot of research to see whether which device is the best. But I think the analog RRAM has its own advantage. One advantage is its speed is very fast. The speed can be as high as a nanosecond. But for some transistor-based synapse, the mechanism relies on the electron trapping detrapping. So this process is somewhat like a flash or CTM. So its speed cannot very high, and also face some endurance issue. But I think we can also do this kind of research to see which technology will win in the future.
Okay, we have a raised hand. Okay, Zhiding, can you speak up and ask a question?
Hey, Professor. Firstly, I want to thank for nice talking, and yeah, I still want to discuss that problem you just mentioned. I think like for a CMOS-based snaps, is that like if we use the CMOS-based snaps, we like several transistors, like there will be several adder and multiplexer in a digital circuit. So this adder and multiplexer will occur really large area, and there's a lot of energy consumption. And also I know that there's like we can add 3 or 4 levels of RRAM to a single MOSFET, which means we can use the like same area to achieve more amount of RRAM. So I think it may be one of the advantage of the RRAM snaps.
Yeah. Yes. Yes. I think so. Thank you.
Yes, and my question is that you mentioned in your talk, we may have that we need to use several converters in the read to make things accurate. But those such converters definitely occur area and high energy consumption, which is not fit with one of our purpose of designing this such RRAM array. So I want to I want to know more about this kind of design of the how we use the DAC and how we better to use DAC and ADC in the whole array. This is my question.
Okay, very good question. In fact, every time I give my talk, someone will ask me about the ADC overhead. So this is a key question. I think this is one of the key questions for CIM technology. But here, I think for the ADC and DAC, especially the ADC, it is still necessary in the current stage because if we hope to do the analog computing, the pure analog computing, in this way it is very efficient. But if if the whole system all use analog computing, we still don't know how to solve the error accumulation issues, because if the data transfer from one array to another array in a pure analog domain, we will find more error source, and if we do a multi-layer network, the error cannot be accepted very large. So in this case, we introduce ADC So with ADC, the data you get the digital data. That's like some digital analog mixed computing. So in this case, we can have more. We can do more on the accuracy recover. So I think the ADC mostly we use ADC to improve the computing accuracy. Another reason is we hope the network can be can support many different algorithms. So in this case, we need to know how to control the data flow from one micro to another. So in this case, we need to use some cache to store the computing results. So now in the current stage, all the cache can only store the digital data. So that is another reason we have to use ADC. In fact, we hope to find a way to replace the ADC and the cache, but now because I'm not the expert on the architecture, I don't know how to do this. So we only use the traditional method. We still hope to see some good work on the architecture design to replace this. I think this is the future trend. And another thing I hope to mention is the ADC is not so terrible. We have already designed this full chip. This chip we already contain all the periphery circuit, including the ADC and also including the training circuit. You can see this is a two-layer neural network. So we have the two parts of ADC. This is one part for the first layer, and below here, this is the another part for the second layer. You can see the area is not so large as the RRAM array, and the power, of course, the power of the whole system is dominated by the power of ADC. That is sure. But we still achieve almost 100 TOPS per watt energy efficiency for the whole chip. So I think the ADC is not so terrible, especially if you do some good design on the low power ADC. Then that is still acceptable.
Yeah, thank you so much. So my last question is same with the Yu Cong already asked in the question board. So what I think that this fabricated process is just the traditional CMOS technology. Just like I mentioned before, like it put several RRAMs just onto the first layer of the MOSFET. Is that correct?
Yes. This is the full CMOS compatible process. For this chip, it's in fact we fabricated this chip 3 years ago. The RRAM lies on the metal 4, of BEOL. And in our recent chip, the RRAM lies on the metal 1, where we use the backend process to integrate RRAM.
Yeah, backend process. Yes. Thank you so much. That's all my questions.
Thank you.
Okay, so does this answer your question, Yu Cong Huang? Oh, okay, great. So we have a last question from, from Zihan. So when talking about the reliability issues, you mentioned that analog RRAM is quite different from a normal binary RRAM and requires a new modeling methodology to deal with the challenge. So could you please explain more about that? So what's the difference between a binary and a multi-level modeling? Maybe.
Okay, I think there's two questions. One is the difference from the reliability view, from the characterization view. There's some difference. Another question is from the modeling view. There's some difference. From the reliability characterization view, for the memory reliability measurement, for example, if you measure retention, you only need to measure the two states, and you can make a prediction whether the two states will go across or not. So you can expect the retention failure time. And for the endurance test, that is very easy. You just set reset, repeat the set reset process until the window disappears. But for analog switching, it is very complex, especially for the endurance test. We still do not know how to make a good characterization, because if you change the conductance little by little and do this full window switching, it is still not similar as the training case. In fact, during a training case, you can see the conductance change, the trend of the conductance change, just like this. Maybe from start from a lowest state and change to a intermediate state and become fluctuate around a target value. Of course, we do not know this value. It's depending on the network, but it does not change significantly. So we don't know on the device level how to do this kind of characterization. So now we only our work we only confine the resistance change in a very small region. For example, you can see these two lines. We confine the conductance within this length and use some very weak set and reset pulse to tune the conductance slightly to do this kind of measurement. But this still not the real case. So we don't know how to do a good characterization for endurance. But for retention, it is relatively clear. We just program the device to different resistance states. We can tune it to every resistance level. We do not care about that. And then we see the conductance change with time. And we need to extract the conductance change with time. We need to extract this equation that is used for the characterization for the retention of analog RRAM. So this is different from the memory application, quite different. This is from the reliability view. And from the modeling view, there's I think the key challenge resides on the retention and the endurance will take a lot of time, because for the normally for the modeling we only focus on the switching process. The switching process only occur in several nanoseconds. So for this short time, we only care about the some atomic or some ion migration. So we can use like DFT, like MD, like some major modeling technology to simulate this switching process. But for reliability, because retention, we need to measure a long time. So if you still use MD, you cannot get the results. Because for MD, if you simulate for 1 nanosecond, it may be require days of time for the computing. So now if you hope to simulate a year's time, of course, it's not acceptable. So we need to find a new way to model this, to simulate this long-time retention and also the long-time endurance. So we need new modeling technique.
Okay, we have a last question. How do you make sure the modeling and the simulation of application are reasonable, and or how to make them more convincing? So I think this is from a junior student. So I can translate it into this. Okay, if you want to publish a modeling paper in IEDM, what do you need to achieve? Something like that.
Yes, because I'm the TPC of IEDM modeling and simulation session. I read a lot of paper, and during the TPC meeting, I know their theory, whether a paper can be accepted or not. I think for modeling work, we hope we can get some verification. We need some experimental data to do the model verification. So this data can be done by by your own group. You can measure the results by yourself. But if your group cannot do some experiments, you can also read from paper. You can see some reference and extract the data from the reference. So sometimes some students send me email to ask some experimental data. So in this case, I can share some. And also sometimes my students always do this. They just use some software to extract the data dot from a figure in the reference. That is okay. And in this in your paper, you just mentioned this data are extracted from another paper to make the reference. So in this case, it's also acceptable. So I think for all the modeling work, this kind of variation is required. If you without any model verification, this paper it's difficult to be accepted in IEDM. Maybe some other conference is okay, but for IEDM, it is very difficult.
Okay, so I see Zhiding raised a hand. Okay, can you go ahead and speak up?
Hey, Professor, just you mentioned in last question, I want to ask in detail, how can we simulate the IO migration, I mean, among the switching process?
Migration.
Yeah, yeah, because I know it's a really huge amount of ions. You see by DFT, but I just how to think how we can.
In fact, our simulation is mainly based on the Monte Carlo simulation. So Monte Carlo simulation is an event-driven method. So in this in the KMC, only when I migrate from one place to another place, in this case we calculate one iteration. If no ion change, we just skip to. So in this case, although maybe the system is very large, maybe contained a lot of ions, but the simulation time is still acceptable. So I think KMC is very powerful for the RRAM simulation because the RRAM nature, the mechanism of switching is caused by the random ion migration. So I think KMC is a good method. But we also use DFT. For DFT, we only calculate some parameters. Then the parameter input to the KMC. So the DFT, we only calculate some activation energy.
Okay, so any other questions? I think Professor Gao has answered a lot of questions. We have learned a lot. Oh, we still have one more. So why are set voltage and reset voltage asymmetric in RRAM? Is there a suitable physical mechanism to explain this phenomenon?
You mean set reset voltage is short?
Asymmetrical.
Unsymmetrical or asymmetrical. Oh, okay. I think this is because the mechanism of set and reset is different. For set process, the mechanism is the generation of oxygen vacancy. So you apply electric field and some ion from the lattice jump out, leaving an oxygen vacancy. So the activation energy is the formation energy of oxygen vacancy. But for reset process, the mechanism is the oxygen ion releasing from the active electrode. Because for set process, you form some oxygen vacancy, and of course there's some oxygen ions in the interstitial. These oxygen ions can be migrate under the electric field, and eventually it goes to the active electrode, and there's some reaction and forming some metal oxide. And during reset process, this oxygen are pulled out from the electrode and then recombined with oxygen vacancy. So for reset process, the activation energy is the oxygen releasing, the energy for the oxygen releasing from the electrode. So there's two different activation energy. So the voltage is not symmetric.
Great. Okay, I think that's the last question. So Professor Gao has taken a lot of questions. So I want to give a special thank to Professor Gao. Thank you so much. Okay. So I think that's all.
Thank you, Qiming. Thank you, everyone.
Okay, if you still have questions, you can send an email to Professor Gao, and I think he will be glad to answer your questions. Okay. Thank you so much. Okay, so I will close the meeting.